Okay, engineers, on this video we are going to solve this differential equation, which is very similar to the problems in the homework, so pay attention on this. Now, in this case we have a composite function as at the end of the differential equation. Alright, so let's make the model of the composite function. Okay, according to this, it says that from 0 to 1 in the time domain is equal to 0, and then it is equal to 1 between 1 and 2, so this is 2 is equal to 1, and then drops to 0 again to the infinite. Okay, so this is the function. Okay, I'm not going to do the Laplace transform of this function using the definition. Instead, what I'm going to do is make a combination of step functions to write this function as a combination of the step functions. Okay, I'm going to use two step functions because this is one, and these two I'm going to write this one. This is, according to this, 0 and 1. This is u of t minus 1. Okay. Now this is 1. Now this is 1. And this is 2. I'm going to make this 0 and then 1. So this is u of t minus 2. Alright? So this is 2 again. Okay. So how are we going to combine these two to generate this one? Okay, what we are going to do is a subtraction. I'm going to do u of t minus 1 minus u of t minus 2. If we do a subtraction, what should be the result? Well, if we do this, this is 0, 0, and then 1. 0 minus 0, 0. 1 minus 0, 1. 1 minus 1, 0. Okay, so that is the function. So I'm going to write the differential equation like this. Second derivative plus y equal to u of t minus 1 minus u of t minus 2. And this is the differential equation we should solve. Alright? Okay, now we have written this composite function as a combination of step functions. Alright? Okay, I'm going to erase this part because I'm going to need it to solve the differential equation. Okay, so if we solve the differential equation, we are going to solve it this one. Okay? So let's apply the Laplace transform. So it's going to be the Laplace transform of the second derivative plus the Laplace transform of y equal to the Laplace transform of u of t minus 1 minus the Laplace transform of u of t minus 2. Sorry for the space, this continues here. Okay, the Laplace transform of the second derivative is going to be s squared capital Y minus s y of 0 minus y prime of 0. And then the Laplace transform of y is capital Y equal to the Laplace transform of this step function is going to be exponential of minus s over s minus the Laplace transform of this exponential minus 2s over s. Okay, let's replace the initial conditions. Y of 0 happens to be 0 and y prime of 0 is equal to 1. So it's going to be s squared. I'm going to factorize the y here, plus 1 times capital Y equal to, here is going to be exponential minus s over s minus exponential minus 2s over s, and then this minus 1 to the other side, plus 1. Okay, let's clear the y. Capital Y is equal to, this goes as a division, so you have exponential minus s over s, s squared plus 1, plus exponential minus 2s over s, s squared plus 1, and then plus 1 over s squared plus 1. Okay, now the solution, y of t This is actually the Laplace inverse of this. It's going to be the Laplace inverse of exponential minus s, 1 over s squared plus 1, and then plus the Laplace inverse of exponential minus 2s, 1 over s squared plus 1, plus the Laplace inverse of 1 over s squared plus 1. Now, this one is very easy, it's the sine of t. But what about these two? Okay, on these two, we are going to use the formula that we saw in the previous video, where you have an exponential on the s domain. Now, before applying the formula, we have to do the partial fractions of this now. Because this and this, they are the same, we can do it together. Okay, so I'm going to do the partial fractions of this. 1 over s squared plus 1 is going to be a over s plus cs plus d over s squared plus 1. Okay, if we use the Heaviside method, the value of a is going to be the 1 over s squared plus 1 when s is equal to 0. So a happens to be just 1. Now on the other side, cs plus d is equal to 1 over s when the s is equal to the I, which is the root, the I imaginary number. So it's going to be ci plus d. If we replace the value of s equal to I, equal to 1 over I. So let's multiply times I and times I in the numerator and the denominator. So ci plus d is equal to minus I, because I squared is equal to minus 1. Okay, so from here I can see that the c is equal to minus 1 from here, and the d is equal to 0 because we don't have real part. Okay, so we calculated the values of a, c, and d. So it's going to be a happens to be just 1, this is 1, d is 0, and this is minus 1. Just making a quick check, minus s squared, okay, yes, it's good. Okay, now what we are going to do is the Laplace inverse of this, the Laplace inverse of this, and the Laplace inverse of this. So I'm going to do it here, the Laplace inverse of exponential minus s, and then this I'm going to replace with 1 over s minus 1 minus n or s over s squared plus 1. Now we are going to use the formula that we saw on the previous video. The formula, it is actually the Laplace inverse of exponential of as, f of s. Okay, clearly the value of a happens to be 1. The f of s happens to be 1 over s minus s over s squared plus 1. So what is the value of f of t? F of t is equal to the Laplace inverse of this, 1 minus the cosine of t. Okay, so the Laplace inverse of this is equal to, is going to be, we need f of t, the shift, f of t minus 1. So it's going to be 1 minus the cosine of t minus 1. So the Laplace inverse of this is just 1 minus the cosine of t minus 1, and then u of t minus 1. Okay, so that's it for that, for this, the Laplace inverse. And what I'm going to do is, for this is the Laplace inverse of only this part. The Laplace inverse of this, as you can see, is exactly the same, except that the a happens to be 2 instead of 1. So the only difference is that here is going to be cosine of t minus 2, and here u of t minus 2. So let's write the solution. The solution, y of t is equal to this one, is this part, 1 minus the cosine of t minus 1, u of t minus 1, and then this part, which is very similar, but instead of 1 is 2, is going to be plus 1 minus the cosine of t minus 2 u of t minus 2, and then plus, sorry for the space, is going to be the sine of t. And that is the solution. Now remember, I didn't make this Laplace inverse because I use the because it's very similar, it's exactly the same. It's instead of being a equal to 1, is a equal to 2. So is this repeated, but here with 2. Alright? And then the sine of t, which is the same, which is this one. Okay, so that is the one example of how to solve these differential equations using step functions. Alright? See you on the next video.